We're going to start examining the biasing and large performance of our source-coupled pair, which we will abbreviate SCP. Alright, so let's draw our source-coupled pair, same as we did before, only we're going to look at the source-coupled pair here with an ideal current source bias. In other words, our current source has infinite output resistance. So we'll draw that ideal current source. We would just note that any resistance that the current source had in parallel with it, Rs, would be equal to infinity. And we're going to look at this with a common mode voltage. And what common mode voltage means is we're going to put an input voltage that's tied to both terminals. In other words, it's common to both the input to both inputs of the differential pair. And looking at the output on both drains of this differential pair. Now, ideally, we'd like for this amplifier to completely reject changes to the common mode voltage. In other words, the output voltage at both terminals would change proportionally, and we would get zero differential output voltage. So, what we're saying is that our DC current IM1 should be the same as the DC current through M2, and in other words, half of this tail current source IS should go through both of these transistors. So we should say that IM1 is equal to IM2 is equal to IS over 2. Because both transistors are changing at the same time, our output voltages VO1 should equal VO2. In other words, our output differential voltage is equal to 0. So if we do a quick perturbation analysis and say what happens if we increase the voltage of VCM, then we would expect that the voltage at the source node, which we'll call node 3, would also increase because it would just be a VGS drop between the two, and if we increase the gate voltage, the source voltage would have to go up as well. So our source voltage goes up proportionally if we increase that common mode voltage. But we also know that the current is forced to stay constant because the current can't be greater than IS through an ideal current source. So no matter what we do to this common mode voltage, the node voltage at 3, even though it goes up, there's no place extra for current to flow but through this current source, so half the current will still go through M1 and M2. And so what we can say about this is that the output doesn't change. Which is, of course, what we desire. And output voltage doesn't change means that we have a constant bias point. Alright, now let's look at another case where our input resistance is not equal to infinity. So we'll look at the same amplifier, but this time we're going to say that the output resistance is not equal to infinity. So here, when we have a finite output resistance, and we'll just say that our output resistance Rs is equal to Rs prime, and it is not equal to infinity, it's equal to something lower. Here, if we have a VCM increase, then we would see a V3 increase. Now, IM1 is still equal to IM2. In this case, we're increasing the gate voltage on both transistors. The source voltage will change proportionally, so the current should stay the same. But what we should note is that the total current flowing through this current source now has to include the current that would flow through the resistance. So what we're going to say is that we have a total current flowing through here that's called IS prime, and IS prime is equal to our original IS plus our increase in V3 divided by RS prime. Now, if we have an ideal current source, RS prime should be big. So we can say, in general, RS prime is big, so the bias point doesn't change much. But we have to note that the bias point would indeed change a little bit. One other thing that we should note is that it's getting harder in scaled CMOS to make these current sources with very high impedances. So what we can say is, as we scale technology down to smaller and smaller transistors, this is becoming less and less true. In other words, the bias point does change a bit. Alright, so in the next part of the lecture, we will look at the small signal analysis. In other words, we're going to try and find what the voltage gain of our source coupled pair is. And we'll find the small signal differential voltage gain and the small signal common mode voltage gain, and look at things like our common mode rejection ratio.